and start defining the coefficient matrix of our problem, which, if you remember, it was 3, 2, and -2 and -1. I don't want it to output, so I put a semicolon, and then I'm going to define the complementary solution. So that's, I'm going to call it xc of t, and that's going to be equal to c times 1 multiplied by 1 -1 times e to the t, and then we're going to add c2 times, open parenthesis, first vector was 1 -1, well, you need to put a semicolon here, times e to the t, but remember that it's also multiplied by t. And then we have plus 0 and 0.5, all multiplied by e to the t. I don't want it to output, so I put this. Now notice here that I made a little bit of a mistake right there. Now I want to declare my symbols, so that's going to be C1 and C2 here, and also T. Okay, so now that we have this, I'm going to check my complementary solution. So to do that, I'm just going to take the derivative of it, and I'm going to set it equal. Equality is given by two equal signs in MATLAB. I set it equal to a times xc. Now, I want it to expand because the result might be pretty big, and then I want it to simplify. And I'll do that both to the left and to the right. Okay, so now I press Control Enter, and I see if we get the same thing on the left and on the right, which we do. So we know that so far we're right. So now, getting into finding the so now we need to define the fundamental matrix. So we'll call it phi of t, and it's going to be composed of x1 and x2. So a trick would be to define x1 and x2 here. So defining my two homogeneous solutions. So then we get x1 of t, that's going to be equal to 1 -1 times e to the t, here, okay? And then look, this is our second solution, right? So I'm just going to cut it, and I'm going to paste it here, calling it x2 right here. So this one, instead of that whole mess, I can write x2, and here I can write x1. Now, why is this interesting? Because now I can define my coefficient matrix just as x1, x2. Notice that here I just have a comma, not a semicolon. I don't want it to output. Actually, I want it to output to make sure that it is the right format, the one I need. And then finding the inverse of the fundamental matrix. Fundamental matrix. So that's going to be, we'll call it pho, and that's going to be the inverse of phi of t. Okay, so now that we have this, remember, how can we finding u of t? Well, we need to take the integral of pho of t multiplied by f of t, but we don't have f of t defined. So let's define f of t up here. So defining the forcing function. So f of t, what is that going to be? Well, remember what it is. The f of t is going to be the vector 2, 1 times e to the negative t. I don't want it to output, so I'll put a semicolon at the end. So now that we have this, we know what u is, and now finding the particular solution, what is that going to be? Well, that's going to be xp of t, and it's going to be phi of t multiplied by u of t. Case sensitive, so we use the lowercase u, so we'll use the lowercase u here. And then we want to check if the solution is correct, is valid. So we do the same thing as before. We would have this. However, now we're going to have a p here. And we're going to have the forcing function as well. So let's check so far how it's going. So we get the right thing, so we know that this is true. So this whole thing worked. And now I'm going to define the general solution. So to define the general solution, I'm going to call it x of t, and it's going to be x of c of t. You don't need to write of t, but I like to just keep that in there. This is going to be the general solution. And if I want to check the general solution, you can just rewrite this, but now it's going to be just x in here. Press Control Enter. MATLAB is going to rerun the whole code, so this is not the most efficient way to do it. And we want to check that we get the same thing on the left and on the right, which we do, so we know that this is the answer. I hope this was useful, and I'll see you next time.